welcome. This is the problem review for AP Calculus AB and BC, Unit 1, Limits and Continuity. We'll be going over both multiple choice questions and free response questions, both calculator active and calculator inactive. Let's get on to our first problem. Since this is Unit 1, and it's mainly a foundational unit, we won't really have any FRQs that really, like any full FRQs just concerned on this topic. And actually that's true for a lot of these units in general, because the writers of the AP Calculus exam like to put together lots of units into one topic and give you an FRQ on that. But you can take parts out and see if they fall into different units. And in this case, we have part A is part of this unit, Unit 1, Limits and Continuity. That's what we have. A 12,000 liter tank of water is filled to capacity. At time t equals 0, water begins to drain out of the tank at a rate modeled by R of t, measured in liters per hour, where R is given by the piecewise defined function. R of t is 600t over t minus 3 for 0 is less than or equal to t is less than or equal to 5. And 1000 e to the minus 0.2t for t is greater than 5. Alright, so usually we'd have a calculator in this scenario. It's obviously calculator active question and do a bunch of calculations, but we really don't need to do that right now, because this is not about solving the whole question. This is just about Unit 1. And generally, these problems don't require calculators. Now, we're asked if R is continuous at t equals 5. Now, let's remember our definition of continuity. We had three criteria. Right? Our first criteria was that f of x exists. Right? Or in this case, R of t. Like, it's an actual value. And our second criteria was that the lim f of x exists. And our third criteria, right off to the side, was that f of x equals the limit of f of x. So with that in mind, let's go through these criteria one by one and see if this function fulfills all of them. Remember, it has to fill every single one of them to be continuous. Okay, is this function defined at t equals 5? Well, we see here in this top one, it's a non-strict inequality. It has the less than or equal to 5, which means this part is going to have the equal to 5. The bottom has t is greater than 5. That excludes 5. So the top part is going to be the one that actually has 5 in it. So we can look at R of t, just plug that in. We get 600 times 5 over 5 plus 3. Now, of course, you can do this with a calculator. You don't have to do it in your head, but if you want to, it's 375. All right, now this is 375, so our value does exist. It's 375. Now we have to find out if the limit exists, right? So we have criteria 1, 375. Criteria 2, we have to find the limit of the left-hand side. Well, that's actually pretty easy since we just did that. We plugged in the value of 5 into the function on the left, and then the function on the top, which is from the left-hand side. And obviously that is going to be our limit, because that's how we define the limit, right? So this, for the second criteria, the left-hand limit is going to be 375. And then for the right-hand limit, even though it says t greater than or equal to 5, not greater than or equal to 5, meaning we're excluding 5, we're still going to plug it in anyway, because that's how we find the limit. Now, if we plug in 5 in there, we get 1000 times e to the negative 1, or 1000 over e. And well, obviously you can use a calculator to figure this out, but it's kind of obvious that this is not going to be equal because 375 is an integer and 1000 over e is not going to be an integer. So these two are not equal. Right? They're not equal. So the second criterion doesn't work. I mean, the third criterion also doesn't work because you can't have something equal something that doesn't exist. And we didn't need to find out the third criterion was true or not because one false criterion is enough to tank the entire thing. So with that, we know that r is not continuous at t equals 5. Now that's just to show the work that leads to our answer. So what you do is you'd show yourself plugging in t equals 5 to make 375, and then finding the left-hand limit and the right-hand limit. Now one important thing that we didn't really show here is that it's always a good idea. It's always a good idea when the problem asks you to show your work. It's always a good idea to say like limit as x approaches 5 from like say the positive side of r of t, right? Because like this notation over here, while you may like know it and have it in your head, if you don't put it down, that sometimes will not count as showing the proper work. If you just put r of t, right? If you say like r of t equals 1000 e, well, that's not true. It equals 375. But what you meant was that the limit as x approaches 5 from the positive side is that. And unless you write that, it confuses the readers and you might lose a point. So just make sure that you write that in. So with that, let's get on to some of our other FRQs. Now the rest of these are all calculator inactive. Not that we had to use calculator on that one either. But let's see what we have here. Now, we do have, it is mentioned that f prime x equals 1 minus natural log of x over x squared. But this is a limits of continuity question. So, doesn't matter, right? We don't care. Right? We're not to that unit yet. And if you look at the question, we're not asking about the derivative. They're asking about the limit. Right? Now, we have f of x is equal to the natural log of x over x. And they're asking for the limit as x approaches 0 from the positive side as x approaches 0 from the positive side of limit f of x. So we need to find this ln of x over x as it approaches 0 from the positive side. Okay, let's think what we have here. Now remember our limit laws when we talked about the quotients and what we get when we divide two limits, and we can see that if we write this as a quotient instead as ln x over x, we can make this the limit as x approaches 0 from the positive side of ln x over the limit also as x approaches 0 from positive side of x. And then we can evaluate these two limits separately and see what we get. Now, if we look at the numerator, the value of ln x as x approaches 0, well, it's not 0, right? Because ln of x is 0 when x is 1. So it's not 0. So think about how we write a logarithmic function, right? If we have our graph like this, we usually write it something like this, right? Something like this. And that's because as we get closer and closer to 0, well, that's like negative powers of e, right? If you have e to the 1, so that's going to be more than 1. That's going to be more than 1. If you have e to the 0, that's going to be 1. And if you have e to the negative 1, that's going to be less than 1. If you want to get a number less than 1, right? If you want to get a number less than 1, then you have to put in a negative number, right? So let me show how I'm thinking. ln x equals y. Right now we can do e to the ln of x and e to the y, right? And that's a true statement, right? This is still true. So get rid of the rule. X equals e to the y. X equals e to the y. And we're trying to figure out what y is, the limit of y. As x approaches 0, as this goes to 0, then y becomes really, really negative. Right? If y is negative infinity, then that's basically saying e to the infinity and then 1 over that. So 1 over e to the infinity. And as e to the infinity gets really large, 1 over that becomes really, really tiny, and that becomes 0. So y is going to be negative infinity. So in the numerator, this limit, it's going to go, it's never going to converge, but it's going to go to negative infinity. As you get closer and closer to 0 for x, y, the value of ln of x, the limit, is going to get closer and closer to negative infinity. Now let's look at the denominator, which is, compared to what we just did, pretty simple. The ln, the limit of x approaches 0, positive side of x. Well, I mean, you can just plug it in, right? You can just plug it in. We didn't do that for the natural log, because the natural log of 0 is undefined, so you can't just plug it in and roll with it. Here you can just plug it in. You just plug it in, you get this is equal to 0. But we can't put 0 in the denominator. But we're approaching 0 from the positive side. It's becoming really, really, really tiny, right? So we're getting something really, really, really tiny in the denominator. Still positive, though. So we can put this denominator, like, just try to illustrate something that's tiny. We can put, like, plus 1 times, I don't know, like 10 to the negative 100 or something. But it's not going to be like anything like that, but it's a way to represent that x is going to be really tiny. Right? Now, think about what we're doing here. We're dividing something that's really large. Well, actually, it's technically really small because it's negative. But if we just pull the negative out for a second and consider it like this, we're dividing something that's really, really big by something that's really, really tiny. We're dividing infinity by what's basically 0, getting close to 0. We're going to get infinity. We're just going to stay at infinity, right? Because, I mean, that's what you get when you divide something that's huge by something that's tiny. You get infinity. Right, so this is going to be, this entire part right here is going to be infinity. Now you have that negative tacked on, so our answer is going to be negative infinity. So this is the value of the limit as x approaches 0 of f of x. It's negative infinity. Right, now with that, let's get on to our next question. Okay. Let f be a function defined by f of x equals 1 minus 2 sine x for x is less than or equal to 0, and e to the minus 4x for x is greater than 0. Okay, and the question is, show that f is continuous at x equals 0. So we just have to run through the process we've been using, right? We have our 3 criteria for if x is continuous or not. We just go through that. If we find the value of it, let's see. This one up here is the one that has the non-strict equality, the one that includes 0. So we plug 0 into there. 1 minus 2 sine 0. Well, sine 0 is just 0, so this just cancels out, and you just have 1. Right, so the first criteria, we have 1. Now, the last time we did this, we kind of wrote it down on the side, but here we don't really have to do that. because last time we were trying to figure out if it was continuous or not, and we needed to keep track of all the numbers to see if it was continuous. Now here they're telling us it's continuous, and they're asking us to prove it. So as long as you like put it in a certain place and just say like f of 0 equals 1, you'll be fine. Now you have to get on to the second criteria. Now the limit as x approaches 0 from the negative side of x is 1. Right? Pretty obvious, since the left-hand side, the negative side, is the one that has it's the one that has 0 in it, so you just plug in 0, it's going to be the same as the value we found. It's just 1. So with that, we can put 1 over here for the left-hand limit, 0 there. And now we have to calculate the right-hand limit. Now, of course, on the AP exam, well, first off, you'll be writing in black or blue pen, so you can't erase it anyway. But even if you could, don't erase your work, because sometimes work will be a bigger part of the equation than just getting the answers right. Right? Many questions give more points for like getting all the steps right than just the answer itself. So that's why you never want to erase your work, not that you could anyway. But just make sure all your work it's easy to read through, it's very neat, and you have all your answers circled so you don't lose points that you should have gotten. Now, let's keep going with x approaches 0 from the positive side. Well, here, we just plug 0 into this e of minus 4 times x. Minus 4 times 0 is 0. And e to the 0 is 1. So this limit right here is 1. 1 equals 1. Right? I think we can all agree on that. And, well, that means that this limit exists, right? The limit exists. It's 1 equals 1. Right? So the limit is 1. The value of this function that we calculated is also 1. Right? And you can write this as like, don't just try 1 equals 1. Right? Write it as like limit. You can write, I mean, if you really want to cover all your bases, you can write it like this. So from the left-hand side equals the limit from the right-hand side equals f of 0, right? And you can show that, right? And that will show that f is continuous at x equals 0, because we have fulfilled all 3 criteria. With that, let us get on to our last practice from our last FRQ. Okay. This one we have 2 parts that are included in this unit. So let's see what we have here. They're asking us for the function f of x equals x cubed minus 2x squared minus 3x over 3x squared plus 3x minus 6. And they're asking us for the zeros of f of x. I mean, looking at this barely even seems like a calculus question. This seems more like just like an algebra question, just to find the zeros. So the zeros are obviously, well, the numerator is 0. So we have x cubed plus 2x squared minus 3x. And if we are going to factor that, we end up with x on the outside times. And then if we take that x away, then we end up with x squared plus 2x minus 3. Now, and that can be factored as x plus 3 times x minus 1. So when any of these terms is 0, numerator is 0. So our zeros are 0, minus 3, and 1. Now before you just stop there and move on, I have to do one critical thing, which is that if you have something that's a 0 in both the numerator and the denominator, it's not really a 0 anymore, because then you get 0 over 0, indeterminate form. And that gives you a removable discontinuity. Right, so if you also have a 0 in the numerator that's a 0 in the denominator as well, you cannot count that as a 0, because it's not, the value of the function is not 0 at that point. So looking at that, let's see if any of these three, 0, -3, or 1, if we plug that in there, we get 0. Well, if we plug 0 in there, we just get 0 plus 0 minus 6. That is not 0. We're good. If we plug in -3, we get -3 squared, 9, times 3, 27, plus 3x, but that's -9, minus 6. That is equal to 12, which is not 0. All good. Now we plug in 1. And 1 squared times 3, that's 3. 3 times 1, 3x is another 3, minus 6. And that's 0. So for x equals 1, we have a 0 in the numerator and the denominator. We cannot declare this. We cannot declare 1 a 0 because it's not a 0. Because at x equals 1, we don't end up with a 0. We end up with a removable discontinuity. We end up with indeterminate form. You can't decide if it's a 0 from an indeterminate form. You can't decide anything from that. So, because it's a 0 in both the numerator and the denominator, 1 does not count as a 0. So our answers for part A are 0 and -3. Now we move on to B. What are the vertical asymptotes of f of x? Now the vertical asymptotes are the places where the denominator is 0. Well, looking at 3x squared plus 3x minus 6, we can factor that out. We can put 3, and then we know that 1 makes this 0. 1 is like x minus 1 is a factor of this. Right? That's what it means. So we can just put that there. And then what? Well, if we look at this, then we have x plus 1. And then if we divide this whole thing by 3, we get x squared plus x minus 2. And then we divide that by x minus 1, and end up with x plus 2. So this is our denominator factored out. Now, vertical asymptotes, the denominator has to be 0. So that's 1 and minus 2. Now, you may have seen this coming, but we have the same problem that we did with the other one in the numerator, part A. If you have a 0 that's in the numerator and the denominator, then it's not a 0, and it's not a vertical asymptote because it's just not, it's a removable discontinuity. But if you have something that's a factor of both the numerator and denominator, it's a removable discontinuity. You can't list it down as a 0, you can't list it down as a vertical asymptote. So -1 does not work. Therefore, the only answer for part B is -2. Alright, and that concludes this video, this review of AP Calculus AB Unit 1, Limits to Continuity. Now, I hope you enjoyed this video. I hope you found it informative and that you learned something. And if so, I'll see you next time.